So we just introduced graphs. We looked at the notion of a connected graph, and we talked about, I believe, bridges. So remember, a graph is just a set of points, which we call vertices, and their connections, which are called edges, the lines, right? And what we want to do, we want to continue introducing a lot of terminology. The next big term is the degree of a graph, so definition. Definition. Or rather, the degree of a vertex. The degree of a vertex. So what we're defining is the number of edges that emanate from the vertex. So, example. Let's find the degree of each vertex in the graph. Not good, not good. There we go. Okay, so here's a picture of a graph. First vertex, second vertex, third vertex, fourth vertex, fifth vertex, sixth vertex, seventh vertex. We have V1, V2, V3, V4, V5, V6, and V7. So what is the degree? The degree is the number of edges that emanates. So the degree of V1, we're going to write deg of V1, so it has what? 1, 2 edges coming out of it, so the degree is 2. Degree of V2 has what? 1, 2, 3, 4 edges coming out of it. Degree of what? V3 has just 1 edge going there to the left, so it's degree 1. Degree of V4, 1, 2, 3, 4 edges coming out of it, so degree 4. Degree of V5, 1, 2, 3 edges coming out of it, so degree 3. Degree of V6 has what? 1, 2 edges. And here's the tricky one, degree of V7. What's the degree of V7? Well, notice it has no edges, so it's degree of 0. Degree of V7 is 0. All right, so let's move on. It's a really useful thing, actually. We want to talk about what does it mean to trace a graph. What can it mean? Definition. A graph can be traced if there is a path that uses every edge one time. Once. So that means you have to cover every single edge, and you're not allowed to double over top of edges or triple. So you're only allowed to use edges once. So basically the idea is you can draw the entire graph without picking up your pencil and you don't repeat any edges. So that's what it means for a graph to be traced. It can be traced. So this was inspired by a problem, a real-life problem. So in the Prussian city of Königsberg, this was back in the 1700s, during the time of the Prussian Empire. The Prussian Empire, well, actually it was the Kingdom of Prussia. It wasn't the Prussian Empire yet. So the Kingdom of Prussia was along the Baltic Sea. It was a small German state, and it was along the Pregel River. So here we're close to the Baltic Sea. We have the famous Pregel River. Okay, and here you have two islands. Two islands. And there were bridges. There was a bridge going from this island to the mainland, and a bridge going from this island to the mainland. And then a bridge going between the two islands. And then there were, on this east island, there were two bridges going northwards and two bridges going southwards. So the city was built along these islands and along the banks of the river. So, very famous mathematician Leonhard Euler. Leonhard Euler, probably one of the great mathematicians of all time. One of the greats. So he posed the question, is it possible to cross every single bridge? So you're walking along at night, cross every single bridge. Can you cross every single bridge exactly one time? And he found out the answer was no, it's impossible. So what he did, he called over here, he called land A to the north, and island B was the western island. Island C was the eastern island, and island D was the southern island. So basically he made the land, he made the vertices, and the bridges, if you imagine these bridges being edges that connect the bits of land. So if you draw this into a graph, here's A, here's B, here's C, here's D. So it turns out that A connects to C with two bridges, so you're going to have two edges going from A to C. And D connects to C with two bridges, so you're going to have two edges going from D to C. A connects to B with one bridge. D connects to B with one bridge, and B connects to C with one bridge. So this was his graph. Now, Euler discovered that it was impossible to cross the bridges exactly one time, cross all the bridges, and cross them only once. So the famous result is called Euler's theorem. Euler's theorem. And it basically says this. It says a graph is traceable. That means you can find a path through every single edge without doubling back. So a graph is traceable if and only if two criteria hold. If and only if Number one, the graph is connected, so it has to be connected. And number two, the number, well, let me put it this way. There are 0 or 2. There are either 0 or 2 odd degree vertices. Odd degree vertices. So a graph is traceable, first of all, if it's connected, and there are either 0 or 2 odd degree vertices. So, if I go back and look at the graph of Königsberg, first of all, it's definitely connected, right? It's connected. Connected, so no problem there, right? But, part 2, let's look at the vertices. What's the degree of A? 1, 2, 3, right? What's the degree of B? 1, 2, 3. What's the degree of C? 1, 2, 3, 4, 5. What's the degree of D? 1, 2, 3. So if you look at the odd degree vertices, there are too many, right? We got 1, 2, 3, 4 of odd degree. The famous result says we either have 0 or 2 of odd degree. So yeah, that's the problem. There are too many of odd degree. So the graph is not traceable. Not traceable. Because there are too many odd degree vertices. Okay. Let's do an exercise. Let's see if we can figure out whether or not a graph is traceable. If it is, say why it is, and then find the path. And if it's not, then say why it's not. Okay, here's an example. Okay, so we're going to have a graph. V1, V2, V3, V4, V5. We're going to connect V2 and V5. We have V6 here. We're going to connect V1 and V6. So determine if the graph is traceable. So first of all, is it connected? Yes. The graph is connected. So we meet that first criterion, right? One of the first criterion that has to be satisfied is the graph has to be connected. Now let's look at the vertices. the degree of the vertices. What's the degree of V1? Well, V1 has degree 2. What's the degree of V2? V2 has degree 1, 2, 3. What's the degree of V3? Well, V3 has 1, 2 edges. Okay, how about V4? How many edges does V4 have? 1, 2. And V5? The degree of V5 here, let's see. One, two, 3 edges coming out of V5, so that's equal to 3. And the degree of V6, you can see there are 1, 2 edges. Now, it's connected, and when you look at the degrees, there are 2 of odd degree, right? 2 of odd degree. 1, 2. All the rest are even. So since there are only 2 of odd degree, so remember, a graph is traceable if and only if it's connected, and if either 0 or 2, there are either 0 or 2 odd degree vertices, so there are 2. So by Euler's theorem, since, well, let me erase that. Since there are 2 odd degree vertices, then the graph is traceable. Okay, let's actually find a path that traces the entire graph. Let's start. So what you want to do when you have 2 of odd degree, 2 vertices of odd degree, you want to start at one of your odd degree vertices like V2, right? And you want to start your path. So here's a path that traces the graph. Start at V2. So always start at one of your odd degree vertices. We'll go to V1. So we got what? V2, comma V1. Then we'll go what? V1 to V6. V6 to V5. There are different ways you can go. We'll go V5 to V4. V4 to V3. V3 to V2, then we'll go V2 to V5, and we'll stop at V5 because that traces, that visits every single edge. So we're allowed to visit each vertex more than once, but we're not allowed to visit any edge more than once. So yeah, that's it. That's the path that traces this graph. There are actually other paths you could have taken.